Hi, everyone. Yeah, good evening. So depending on where you are in the world, could be good evening, good morning. So I'm here in San Francisco. So for me, it's 7:30 a.m. So it's morning. And if you're in Europe, it's good afternoon. Akshay, you're in India, I guess. Good evening. All right. We let's wait a few minutes, get more people in. If you're already seeing the webinar, say a quick hello in the chat. On our side, you see Chinka, Nidhi, myself. Right. More people joining. Hi, Ankit. Hello. Hey, everyone.
Hello.
Who joined the first part of machine learning modeling? Anyone has seen the first one? Okay, Ankit, you joined. Great. Welcome, welcome. Yeah. Okay, I would say more people will join. Let's get started. So yeah, officially welcome to our webinar. It's the second part of machine learning modeling. The first one we did last week. And this time we got really good feedback after the first webinar. And we said like, hey, why not making a second part and actually going to be a little bit more advanced? Because some of the feedback we got from people where, yeah, it was great, but sometimes also a little basic. We would like to learn more, would like to know more. So we got together and set up that second webinar now. Yeah, some of you joined already last week, so they know us, they know what we are doing, what data-driven science is. But for all of you who it's the first webinar, I want to give a quick overview about the company and also the team. So data-driven science, or DDS, is a artificial intelligence training company. So we started late last year, and we create content around data science, AI. And we are currently working on our first comprehensive machine learning course, which will be published soon. But besides like online courses, we also create or want to create more content, either articles or videos we publish across our social media channels to help people learn more about data science and AI. It's a very exciting topic, very hot topic. And we want to create our educational resources a little differently. And our main focus for all the content we create, either it's video, online courses, webinars, blog posts, and so on, we really want to focus on understanding, thought process, and practical application. Because what we believe is that many of the content creators out there are not focusing that much of understanding. It's more about just learning the syntax of machine learning, learning the algorithms, for example, but less about really understanding the big picture. And this is what we want to do. We want to give you everything at your hand that you need to solve any project in your real life, in your personal projects, at companies, and so on. And we really hope you understand, or you also see that we approach education, AI education, a little differently. The team of us, like we are 4 people. It's Achinkya, and Achinkya will lead the webinar again. He already did last week. Then there's Nidhi, Prakash, and myself. So the 4 of us are data-driven science, and we create the content. All right, so I hand it over now to Achinkya, who's gonna kick it off and talk more about machine learning modeling.
Awesome. So just let me share my screen. Jan, just can you let me know if my voice is audible?
Yes.
Awesome. Perfect. So these are the stages of machine learning. And last time when we were talking about basics of machine learning modeling, we just focused on simple understanding of what a machine learning model is. Okay. Today we are going to go a bit hands-on and deep into the ML modeling part, where we'll see different ways we could run different algorithms on let's say same data set, different kinds of data set, what are the factors which actually affect the accuracy, how we could improve the accuracy, all the stuff which actually makes an advanced data scientist. That's what we would actually focus on today. So it's not just about basics now, it's about actually taking it and completing the POC. So what is a POC? POC is nothing but the product which proves my machine learning model works. So if the business decides, then it is going to be taken up to be implemented in the company. So before we move to the POC, we have to actually prove and get a good accuracy, and that's why that stage is essential. So we have to do this ML part very well. So it is said that amount of effort, which amount of time which goes into stage number 5 is 20%. Okay. But the amount of importance stage 2 has is 80%.
Achinkya?
Yes.
The mic, we get some comments that it's not loud enough. Can you speak a little louder or closer to the mic?
Okay, so how about now? How's the voice now?
Oh, it's better for me. Guys, can you say in the chat whether this is better now for you?
So yeah, testing 1 2 3, testing 1 2 3, and is it okay now?
Oh, it's
Okay, it's
better.
better. So my headphone plug is not working, I think. So let me just use the laptop microphone. Okay. So I was saying, in terms of time spent, in terms of time required, the ML modeling part takes only about 20%. The rest of the part kind of like goes in highly into this phase, which is the ML data preparation for the ML modeling. So if it were to be done, so it's like data preparation, stage 3 takes in a lot more time than the ML modeling. But in terms of importance, the machine learning modeling is very important, and feature engineering is very important in terms of final impact. Even though most time is spent on data preparation, and let's just say some other things which we might do make the data ready for the final ML model. So because importance of the ML model is second highest to only feature engineering, we have to understand it pretty well. And we can't just skip it. We have to know how to do this end to end. Okay. So we are going to see this ML modeling part, and then we will go into more details of rest of the stuff. So before that, I just want to focus on this part, which is data science is right now not an exact science. Okay. Before a science becomes science, it is an experimental science. So for example, Newton's theory, any theory in physics or something, there is a hypothesis. And how do we prove that? We actually run an experiment. If that experiment disproves what we think, then it is disproven. Okay. If it does not disprove, then it doesn't mean my theory is proven. Okay. We have to do lots of experiment, and then only finally we can conclude this is a universal law. Okay. In science, there are two types. We have a experimental science, and we have a science which has explanation, something which we can derive, something which we can completely explain on the mathematical, for which we don't need a laboratory. Okay. Whereas in data science, it is more like an interactive thing. We try something, we see what happens. Then after we check what has happened, then we try something else. So we are constantly trying to find out what is a better way or what is an answer in my case. And that is why data science is an experimental science. Right now, we don't have an explanation towards why something works better. We might not have an explanation about why this model is the best choice, but we have to find out which model is the best choice. Okay. So we have lots of libraries which have been pre-implemented to make that job easy. Okay. Even though it is experimental science, we have a lots of apparatus which has been created for us to help us into doing that. But if I don't understand that apparatus, then I am actually like a blind person trying to do this. Okay. So the libraries which have been implemented, these libraries are amazing. They implement a lot of stuff beforehand. Everything is implemented beforehand. The problem is if you don't know what you're doing, it's like having a gun, giving a gun to the monkey. Okay, don't be monkey. You have to understand the power of the tools, what the tool is doing, how it is doing, what are the consequences of a certain choice, what are the better alternatives to that choice. All of these things we have to actually understand. And when we understand that, that is only when we know what we are doing. Okay. We want to do informed experimentation, experimentation which is following a scientific methodology, experimentation which learns from what experiment you have concluded. So you have to know what you're doing, and only then the ML modeling is actually can be called as a good ML modeling. Okay. So the way it works is like this. So let's just kind of like go to the code directly, and let's just now exit the slide deck. Let's go to the code. And in this code, now let's just see, execute the code here. Okay. So we are going to begin with machine learning modeling. And in ML modeling, we have data and we have model, right? So in first place, let's create some data. And to create the data, we are going to use a machine learning, this thing from API reference. Okay. So I'm constantly going to keep this API reference with me. Okay. So I know that there are some data set utility creators. So let me just search data set and let me find out the utilities which allow me to create the data set. Okay. The reason I am coding in front of you by looking at documentation is because this is how you will do it. Okay. When you are starting from scratch, it is likely that you will not know the function, you will not know the important parameters. So always you'll have to, look up the function, look up the documentation, look up the syntax. And that is why I would really recommend for you to have this API reference open. Okay. So here we have what we have. I want to create data for regression because it is always easy to understand. So let me use this make regression. Okay. How do we use make regression? Now it's where is it present? It is present in scikit-learn, then in data sets. Okay. So let me code that here. So from sklearn dataset import, and what is this function we are importing? Make regression. So I'm importing this thing and I'm going to execute this. Okay. Because you are going to be coding from scratch almost all the time, I would really recommend everybody to create their local this thing in a certain manner. So I would suggest always use Jupyter Lab. Okay, then do right click and open show contextual help, and in the contextual help, make it on the right hand side. Okay, and minimize that a bit. Then right click on the notebook and create new console for the notebook. Okay, and then move this here in this half of the notebook. So you see what happens is you now actually have three things with you. Here on the top right part, you have a place where you can see help. Okay, here on the left hand side, you are doing coding. Okay, here on the bottom right hand side, you actually have a console. So for example, okay, if I say x is equal to 3 and I execute this, okay, now if I do print x here in the right hand side bottom part console, this Python thing is connected to my notebook. They both share a stage. Okay, so if I want to do some experimentation, a good place to do that is here on the bottom part. This is nothing but the same notebook, but it's just that the code doesn't go here. So if I want to do some ugly experimentation, I can do that in the bottom right part. If I want to check the documentation, I can do that in right hand side top part, and my code goes here. Okay, so I'm going to delete this, and what we have done is like we have created a make regression. Now I want to create a regression data, so I'm going to say make regression something. Okay, now I can press shift tab. Okay, I can press shift tab, and if I do not give any arguments, these are the arguments which will be taken by make regression. Okay, now looking at this, it is going to say a number n sample means how many samples do I need. Now let's just create a much bigger this thing. Let's just create 10,000. Okay, now what? Let me press shift tab again. I don't need to press shift tab because it is available here on the right hand side. That's why we should have this contextual help ready. Then number of features is how many columns do I want to have. It is regression. Let's just have 2 columns. Okay, let's predict z variable based on 2 x and y variables. Okay, now here an informative is this thing. What does an informative say? Okay, what does an informative say? An informative says how many of these 2 features are actually going to be used in finally doing the prediction of what we are trying to predict. Okay, so if I choose an informative as 2, it means whatever I am predicting, okay, it is actually contains 2 columns which are used in predicting that. Okay, so if I change that, and I make it 1, what happens is, oh, now in this scenario, right now, how many columns do I have? I have 2 columns. Out of 2 columns, what happens? Out of 2 columns, only 1 is informative. Means 1 is noise, other is not noise. So that's pretty interesting to know. Okay, so we have an informative. Okay, fine. Then let's just say, let's take some noise. Do we have noise here? Yes, we have noise. So I'm going to add some noise. Let me add 10, some standard deviation noise or something. Okay, let us just, this coefficient. Remember, this is linear. It is regression data, so it is like a slope and intercept. So I am going to say coef equal to true. So it is going to actually return the coefficient of the data it has created. Okay, so this I have experimented and I have found out this is how it works. Okay, so this is how you can actually learn it yourself. So how do you do the experimentation? You do the experimentation with help of documentation, with help of this thing which is on the right hand side. You have the below that you have experimentation thing, and with help of these things you actually learn how to do it yourself. So I am going to choose number of features as 10,000, number of features as 2, number of informative as 2, noise is equal to 10. Okay, and I'm going to say random state is equal to something. Random state is nothing but a seed. As long as you execute the seed with same random state, anybody will get the same output. Okay, we are creating random data here. And if the random data is different every time, then it's a stupid experiment. It is not repeatable. So anybody who executes the same function call, no matter where they are, they will get the same output. Okay. So let me just do that. And let's just, format it in such a way that it is visible in one line. Okay, fine. The number of samples, number of features, let me just put it into one thing. And let me just put that noise this into one line. Okay, so I'm going to execute this. Anybody who executes that will see the same output no matter what you do. Okay, so what is it returning? It is returning 3 values. So I'm going to say X, Y, and coif. And I'm going to execute this again. So now what happens? X contains the training data, Y contains the prediction, and coefficient contains the coefficient. So it's like, if I just say X dot shape, there are 10,000 rows. There are 2 columns. When I say Y dot shape, there is only, for corresponding value for these 2. This is how this thing is. And if I say coef, what is the coefficient? This seems like, I don't know if it is a linear this thing or not, but maybe we can plot. Right now, I think we have chosen 3D. So if I choose n features 1 and informative 1, then number of shape is going to be this thing, 1000 into 1, Y shape is equal to 1000, and maybe we can plot X and Y in a 2D graph. Okay, I'm not going to do that. I'm going to keep number of features is equal to T, number of informative is equal to 2, and let's just, proceed further. Okay, so let me delete this. This thing we should have done here. X dot shape, what is X dot shape? It's something. Okay, so this is how, and let me just see if I can selectively, no, I can't selectively zoom out just this part. Would have been fun if I could do that though. Anyways, okay, now let's just see on this thing. I want to apply an algorithm, and let's just see. Let's go to API, and let me start with linear regression. The API reference, I mean, of course, I could code this without needing to take a look at the documentation, but I'm not doing that because I want to show how can you, who is just beginning, how you can kind of like use documentation to help yourself. So you see this linear model is present in sklearn. Okay, so I'll say from sklearn, then it was in linear model, and then I want to import linear regression. Okay, I'll execute that. And now what's my model? Okay, model is equal to linear regression. And I'm going to start open this thing. And here on the right hand side, help has automatically come. It is saying normalize. There are few parameters. Okay, there are no parameters needed. So I'm going to say model is equal to this thing. I'm going to say, train that model. So I'm going to say model dot fit x comma y. Okay, and then I'm going to do model dot predict on x, and which is y predicted. And after I have done the y predicted, I actually need to find out how good is my model. Okay, what's my error? Okay, so error, where is it? Error, where is the error present? Error is called as nothing but matrix. Okay, so if I find out where are the sklearn matrix, okay, these are the matrix. Not matrix, matrix. Okay, in regression matrix, what I'm going to choose, okay, maximum error or mean absolute error. I think mean squared error is a better choice. There might be some situation where log might be a better choice. Here it is definitely that mean squared error is what I'm trying to, let's just say, use to see how good my model is. So I'm going to select mean squared error. Where is this mean squared error? It is present in sklearn in matrix. Okay, so I'm going to import that. So I'm going to import, I'll put it here. So from sklearn matrix, import mean squared, I think it was error. Let me execute this, shift enter, it's been executed. Okay, so now let's just calculate what is the error. So how do we use mean squared error? On the right hand side, we check the documentation. Okay, we give an input as what is y true, and y true is what? Nothing but what was the actual observed data, and what y pred is what was the predicted data. So I'll say mean squared error. Here the first parameter is observed data, okay, and second parameter is predicted data, okay. So I have to remember that, okay. So you see in even model.fit, first parameter is the x, and that second parameter is the y thing. So if I don't want to actually do that, if I don't want to actually do that in the model.fit, what I could actually do is like, let me just press shift tab here. Oh, I have not executed. That's why. Okay, when I execute, this thing should give me the documentation immediately. Okay, so when I call model.fit, it actually shows me what are the name of the parameter which is being passed. And in the way I did in the bottom, in the this line, okay, we can actually give in our parameters and we can explain them. So this first variable is number of samples. So you see, I have actually taken that n samples and mentioned it here equal to. So whenever I read this function call, I actually understand that it means this is number of samples. So then, when I do it like this, I could, move my param arguments around. It is easy to read. It is immediately easy to understand. I can move them. So here in model.fit, let me just do that. X is equal to this, and then Y is equal to this Y. Okay, now I'll easily understand. First is X, second is Y, and in the predict thing, it is also X is equal to predict. And what is in mean squared error? The first thing is Y underscore true is actual one, and then Y underscore pred is the predicted one. Okay, so mean squared error, and that's it. This thing actually gives me what is the mean squared error for my regression data using 10,000 examples which I've created. Let me make it 100,000 and let's execute. Let's execute the model again and let's see what's the error. Error is same. Let's make it. Let's add one more zero. Let's check. Error is the same. As you can see, no matter how much, let's say, data point we add, the error is accuracy is not changing. So let's just go on the other side. Let's just reduce it. Let's make it 100, 1000, and let's check what's the error. You see, error is decreasing. Let's make it 100. You see, error is decreasing. So now the question here is pretty simple. Okay, question here is, which one is better? Should we give less data or should we give more data? That's the question. So can you in the chat tell me which one is better? Having 100 is better or having 100,000 is better? Which one do you think? Less data is better or more data is better? Less data is better or more data is better? What do you think? More data, but more data is actually giving me more problem. It is giving me more errors, and maybe it is also taking more CPU cycles to execute. Why is more data better then? You see, this is what experimentation means. Okay, we have to, in each case, we have to actually understand what's the data, what's the complexity, and for that we have to actually find the suitable model. When the data complexity is low, when the data complexity is low and the model complexity is high, that is when we are overfitting. The meaning of overfitting is actually remembering the answer, not learning to find the answer. Okay, so in terms of machine learning, what happens is, the model is best on what it knows. Whenever a out of syllabus question comes, the model cannot answer that. Or whenever a different question comes, the model cannot answer that. So overfitting is like remembering the data. It is not learning the patterns in the data. Now, when the data complexity is high and the model complexity is low, it means model doesn't even learn anything. Data is so complex that we need actually complex models to actually understand the patterns in the data. But we don't have that. That means it is underfitting. So based on the situation, it's either going to overfit or underfit, but no matter what, we have to match the complexity of the model to the complexity of data, and that's why we have to understand the data. Now, if we take a look at this problem statement, the code which we are executing now, and in this code, what is happening is the data is very simple. And because the data is simple, even if I add in more data, I'm not actually getting any improvement in my accuracy. Okay, because the model has learned, it has got enough data so that it doesn't need any more data. So for machine learning and deep learning, of course, we need enough data. But beyond that data, no matter how much data do I add, it does not make any addition. Okay, so sometimes we need to have more data, and but many are cases, if adding more data doesn't improve the accuracy, we need to stop our data collection maybe, or we don't even need to take more large data into my machine learning model to train that. Okay, so going back to this thing, now let's just think about what is overfitting and underfitting, which is here. Okay, so how do we check what is overfitting and underfitting? Okay, so overfitting and underfitting is kind of like this. How do we have exams? Okay, in the exam, we generally, for preparing for the exam, we have a final exam is a test. Okay, so that test is actually checking how's our knowledge. And there is a practice exam. Okay, the questions in the practice exam are not really present in the final exam. Okay, but if we have actually learned well and we can solve the practice exam well with help of my understanding, then we should also get good score in the final exam, right? So high score in final exam and high score in practice exam means person is good. So that situation is this. Oops. So high score in practice exam. So what is practice exam? Practice exam is nothing but training. And the final test is the final testing thing. So high score in practice exam, that's his high. Okay, then high score in final exam as well. That's the perfect thing. So now score means less error. Okay, high score means less error. So the example which I mentioned was this. So low error or high score, optimal fit. If I get really high score in practice exam and really low score in final exam, so instead of score, let's just say error. So I make less mistakes in practice exam, but a lot of mistakes in final exam. It means I'm overfitting. It means I have not understood the concepts. I have not understood the patterns present in the data. I have simply remembered the complexity of the data. I simply remember the answer. So this is nothing but rote learning, right? When you have simply done rote learning without any understanding, this is what it means. So in machine learning terms, it is overfitting. So let's say I make high mistakes in the practice exam and low mistakes in the final exam. Okay, I make very high mistakes in practice exam and very low mistakes in the final exam. Either it is luck, I got lucky, but that luck might work in a multiple choice option. But when there is a proper theory, it's not possible to actually make a lot of mistakes in practice exam and very less mistakes in the final exam. So this is actually not possible. Okay, so this thing is not possible in machine learning as well. And if I make let's say high mistakes in practice exam and high mistakes in the actual exam, it means I have not studied at all. So no study is this. Okay, so in the exact same manner we have in machine learning. What we do is like we take in data, we divide that into two parts. One part we use for training, one part we use for testing. The training, the error on the training is called as training error. The error on the testing is called as testing error. And whenever training error is low and testing error is low, that's when we have found the optimal fit. So you see in the data complexity doesn't change. So we have to start from model complexity low to high. So we have to start from low and we have to experiment and we have to go until we go to the higher complexity model, and we want to stop at a place where training error is also low and testing error is also low. That is how we find optimal fit. This is what it means to do machine learning experimentation. Okay, we try out different algorithms. We don't try out all algorithms. Every data scientist might have maybe toolkit of maybe 10 12 algorithms which he has understood very well, and that data scientist will only maybe use those. So different people will have different toolkits, and they will only use that toolkit to kind of like simply solve the problems they are facing. Okay, so that was this thing. Now let's just go back and let's just do that in code. So it is training, testing, split. So I'm simply searching split. Again, why am I doing this? I know the syntax. Excuse me. I know the syntax. Okay. So I could easily type it immediately, but I'm doing this so that we learn to how to find it out for ourselves. Okay. So here we are saying, okay, let's just do this. Where is it present? I want to do train and test split. Oh, this is the model selection. Where is model selection present? In sklearn? Okay, so I'm going to see from sklearn dot model selection import. What was the function name? I forgot. Train test split. Train test split. Okay, and after I do that, I want to execute this. And here let's just say train test split. Okay, and now on the right hand side, it is gonna tell me documentation. So this documentation is not that great. So I guess we'll have to experiment. So to what do we give to train test split? We give x, y, and size something. Okay, so let's just give what is my x data. X is x. So x comma y, and we give random state is equal to, let's say, something, and we give let's just say, what was it? Test size is equal to something. Okay, so test underscore size is equal to 0.1. Okay, so you see what this means is like 0.1. If the data had one example, then 0.1 example would be used for testing purposes. So training error is this and testing error is this. Okay, so here it's like simple thing would be instead of one example, let's take it 100 example. So out of 100 example, 90 will be used for training and 10 will be used for testing. So this is what train test split is doing, and now how it's going to return. It is going to return data into x underscore train, y underscore x underscore test, then x underscore y underscore train, and y underscore test. This is how it's going to be. I know that because I have experimented with it before. How can I find that out? Let's just find it out through experimentation available here. Okay, let me do x underscore train dot shape. The shape is 90 examples and 2 columns. Why do we have 90 examples? Because I think we executed for this thing only 100. So I'm not going to keep it 100. Let's keep it 10,000. Execute this and execute this function again. And let's call x underscore train dot shape. Out of 10,000, 9,000 are for x training. Then let me do x underscore test dot shape. So you see there is 1,000. So you see what that's the meaning of x test size. If I make it, instead of this thing, if I make it 0.5, it means 50-50 division. Okay, if I do x underscore train dot shape now, you see it is 500,000. So that's the kind of like meaning. Many a times algorithm need a lot of data. This algorithm is not cleaning a lot of data for it. Maybe 200-300 rows are more than enough. But many other times algorithm needs lot of data. That is why generally 80-20 division is done. 80% of data is used for training, 20% of the data is used for testing, and we are going to follow the same convention here. Okay, let's just execute this and let's move on a bit forward. So I'm going to use the same algorithm and I'm going to say, okay, let's just call the same algorithm. So model is equal to linear regression. We are going to say model dot fit on x underscore train, y underscore train, and we are going to evaluate mean squared error on y underscore test and model dot predict on x underscore test. That's the code, the training data and predicted value of this thing. Now this will print the what is the mean squared error of my situation here, and let's just execute that. You see now the error has increased. Now the error has increased, but this is the actual real number of error. Here, because we are using linear regression, I think maybe it is unable to find out if whether it is it could be the case that it is not actually linear. Okay, so let's just go for other algorithm, which is I don't know which algorithm should we see. Linear regression is one thing. Then maybe let's go through API reference and let's just go through regression. So what regressions are present? It's like, okay, k-nearest regression we could do. It's not linear. Linear SVC, let's not do that. Then we have SVC, SVR. Then we have decision tree. Ooh, let's just use decision tree. Okay, so I'm going to use this sklearn tree. So where is it present? So from sklearn.tree import. I'm taking a look at the title in the Chrome window. And that's where I'm typing from DECERSON decision tree regressor. Okay, I'm going to execute this. This thing has executed, and I'm going to create model is equal to decision tree regressor. And there are certain parameters here. So I'm going to choose, I'm going to choose all parameters as default. So let's not just go around changing that, and let's just call training on it. So model.fit. Okay, let's do this thing. Okay, let me create a function f train and evaluate. And let's take a model as an input to this function. And in this, we will do this. Error is equal to this thing. And let's just say print as error. Okay. In Python, it is passed by value. So if I give in my model here, it is actually going to copy the model thing. It is not going to do the pass by this thing. So it's a reference value. I think model is going to be a reference. The reference is going to now I'm not sure, but let me just return the model slash error here, and let's just see what happens. So now I've created a function. Okay, so now what happens is, like, now I'll simply call this function train and evaluate, and I'm going to say to this train and evaluate, I'm going to give in the tree model. Okay, so now let's just see vars of tree. Vars of tree will give me what is the detail present in this vars of tree. As you can see, I was right. It is passed by value, so the original tree is not updated. So I need to actually update the tree thing. So okay, so tree is equal to let's just say this. Return the model here, and let's just execute this. And now when I say vars of tree, and dir of let's say tree. This should, vars and dir are the functions which are very useful. They kind of like give us a lots of details of value. So set params, okay, get params is the function which we need to use. Get params is very important. It is always the same thing. Tree dot get params. Execute this. These are the parameters. Oh, unlike linear regression, we don't see any other things here. So there of tree, and in the tree, let's just see, apply alpha, class weight, criteria, decision tree fit, get depth, get params, max features, number of classes, predict, resort, score. Okay, I think score is going to be the one which is going to say how good is my model. Okay, tree dot score, let me call this. The score is actually a function. So you see, we do experimentation like this. I had not done this for decision tree. That's why I had to spend this time in front of you guys to actually do this. But this is how we do experimentation. So let me just say, delete this vars of tree, delete this thing, and the error in this case is higher. Okay. So there are two possibilities. There are two possibilities here. So either the linear was good or this decision tree is good. If we go to this matrix now, what's happening? So what happens is, like, now I think in linear model, the training error was less. But in complex thing, the training error was high. Okay. So actually what happens is more complex. Okay. More complex this thing, the function comes. Let me just insert another table here so that you can understand that. So data, let's say training error, and model complexity. So generally, as model complexity goes higher, where is the insert? Okay, it's like I'm supposed to have a split cell, number of columns, number of rows. Damn it, not this one. Okay. Just a second. Shift enter, no. Alt enter, enter, control enter, no. I don't know why is this adding row not visible here. So I'm simply going to skip this and assume low, high, highest. So training error generally decreases with model complexity. So here the training error is increasing. Okay, it means probably the data is more complex. Okay, so if the data is more complex, then we actually need more data to actually experiment that. So here, let's make it bigger data, and let's just call this thing, and this will take more time. Okay, error is still high. So training, oh, sorry, testing error. Testing error is high, And let's just say what is the training error. Training error we can maybe print out in decision tree. So decision tree regressor dot score, and what was the x underscore train and y underscore train. This should be underscore score. Wait, this is overfitting quite a bit. So you see now data is high enough, and when the data was high, here the testing error is low and the testing error is high here. It means it is overfitting. You see, now what is the training error? How do I print that? Let me open the documentation and let me just see how we can print out the training error. Not cross validation score, methods apply, get path, get leaves, get param, get score. Return coefficient of this thing. How do we return the score? Decision tree regression. So this is how the kind of like experimentation is. Okay, you kind of like start by thinking of the questions and possible explanations, and then this is how you proceed. So this is very important. So the experimentation is very important. Okay, so I want to emphasize a lot on this thing. You have to run your own experiments so that you develop your own understanding. You create a data, use data creation functions. You create your own data. So try out using small data, see what happens. Okay, try out using big data, see what happens. Try out using noisy data, see what happens. Try using something else, see what happens. When you constantly keep on doing stuff like this, that's how you will kind of like understand the intuitively how a algorithm actually works. Okay, you have to constantly keep doing this, and this is how you will truly understand the meaning of it. So going forward, for different algorithms, you have to execute all of this. You have to execute and try out different stuff for all the possible situations. Okay, so run your own experiments, develop your own understanding, and try to do all this going forward. So how do you learn the ML algorithms? This is what our question is. So first, shortlist few algorithms. What do I mean? There are more than, I don't know how many algorithms there are in scikit-learn, but they are upwards of maybe 50, 60 definitely. So you can't possibly understand all of them. So maybe shortlist a few. You can choose maybe 10 algorithms, 6 algorithms, maybe start with something, but shortlist a certain number of algorithms, and then you have to truly understand them. So you try it out on those algorithms. You try what happens on the small data, which parameters are important, what is their meaning. Then search online, see how the algorithm works, see how it is implemented, see details like this. And when you see details like this, that is when you truly understand how the algorithm functions. Maybe you might want to even see the algorithm implementation in scikit-learn library. If not, there are lots of GitHub implementations of the algorithm which are simple to understand. Okay, maybe let me just search that here for you. If I do GitHub, so we are using one machine learning from scratch library. There are lots of machine learning. This one is minimal thing. So here you see, you'll find these libraries are quite popular. Okay, they are short implementations of the machine learning algorithms, and maybe you can understand them better. Oh, this one is directly using scikit-learn. This is it's not from scratch. Okay, this is useless. I think this one is from scratch. So here linear regression, whatever it may be, wherever it is, maybe. But yes, you always have to use Google. You find out what one is good, what one is not. And this is how you keep on going forward. You keep on learning. by running such experiments. Okay. So just a second, let me find the browser. Where is the browser? I think I've closed it. Yeah. Okay. So this is where we were at, decision tree and this thing. And now let's just continue with what we are going into more details. Okay. So going forward, let's just try to try out different things here. Here, training error was high, testing error was high, so it was overfitting. Probably it is this thing. Now, now let me select, instead of number of features as 2, let me choose as 20. And let's make number of informative as 5. Okay. We have chosen as 20. Number of this thing as, okay, data is too big, let me just make it 100,000 and let's just execute this. We have very big data, out of which only 5 are informative. Okay. So let me just do the train test split. This function is executed. Let me execute this decision tree. Okay. And when we execute this decision tree, on decision tree, there is this variable which is called as feature importance. Okay. So this feature importance, I know that because I have checked it inside the model. Now, if you want to find out, let me just print that. So if I simply say tree dot feature importance, yeah, okay, importances. And this is saying what is the importance of feature. Now let me just set up the I want to set the precision permanently to this thing set printing. I'm trying to find out what's the this thing. Okay, let me skip that. But as you can see, instead of 20, let's make it 10. Easier to this thing. So execute this and let us just execute this thing again and print this thing again. So out of 10, okay, 10 is also too much, but still fine. So in terms of feature importance, a lot of features have 10 raised to minus 4 importance, and there are some one which have low. So this one is higher importance. This one is higher importance. This one is higher importance, and this one is higher importance. Out of all of them, you see what's the meaning? We created this thing as 5 informatives, and my machine learning algorithm figured out the 4 features are more important than the rest. So you see this kind of like understanding. Okay, using decision tree, we can find out what are the important things. So how could I have found this out by experimenting on my model? Okay, where's of trees? Let me just do that. Data depth, features, random state, class weight, something. Okay. Inside where's of tree, let me do where's of tree underscore tree. Okay, so I don't know what this var tree underscore tree is. Okay, this is a class. Let me just print out type of this thing. This will say it is a tree class. Okay, fine. Let me do vars. No. Let me do dir. Okay, so there are apply capacity, feature, impurity, depth, this thing, weighted value, predict. Maybe I can call get parameters here. The reason I'm trying to do this is, you see, you don't have to remember everything. You can actually find out what is important. Now, I don't know where that, this variable is hidden. I'm calling it on dir of tree. Now it is saying, okay, get param name, estimated type, validate tree, cost of something. Oh, you see, it was present here in feature important. So I could have gotten this thing. So here, if I read, there is something called a score. We have splitter, we have underscore tree, we have this thing, number of errors, we have feature importances, we have alpha, and blah 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 blah. As you can see, by using feature importance, we kind of like simply understand. Now, excuse me. Now let's just try different things. Out of these, let's just try to find out what kind of features are important. Remember what we try to do here, using decision tree, we try to find out which features are more important. Okay. Let me just ask, is this becoming too complex? Can you please type on the chat? Can anyone type on the chat? Is this becoming too complex? Anyways, it was supposed to be a bit of advanced machine learning thing, wherein we go deep into scikit-learn implementations. So, but still, how is it going? Fine. Okay, fine. Let's just, continue. This is what happens when things become complex, right? So let's go to API. Okay, and inside API, I want to select features. So feature selection, I have searched. Feature selection kind of like opens in a different module. There are these many types of feature selections. Out of these, I can do recursive feature elimination. This is what it means. So it tries to find out which features are not important. Okay. And what is this thing? There is select k best. So for k best, we have to tell it how many k best we have to give. Okay, if I check important, I have to say select k best and I have to say k is 20. So you see, if I don't know the k, I am actually unnecessary including lots of stuff. Here, because I created my data, I know number of informative are 5. But if I don't know how many informative are there, then I might say select 50 best. That's the wrong thing. So I need to find out what is the best k value for this situation. This thing is called as hyperparameter search. Okay. How do we do hyperparameter search? Let's just go to API and let's just try to find it out in front of you guys. Hyperparameter search. You see, this is parameter, this thing, grid search CV. We could kind of like search anything out of this, and this will tell me how to do hyperparameter search. Okay, so I'm going to find out how to do this. So I'm going to use maybe randomized search CV, maybe. Okay, that works. Randomized works nice. So which one is randomized search CV? Okay, let's just. What I want to do, why am I trying to do that? Because I want to find the best K, right? So this is multiple fold thing which I'm doing. Select K best. If this is what I did. So I want to find out best value of K. Okay. And for that, I'm trying to just do this. I wonder if this thing works or not. Estimator is this thing. No, this is going to be brute force. I don't think this can work. I don't think this can work. Shape select K best. No, this can't work because this is like a nested thing. Grid search is only works on a model. Okay, we have a feature selection thing on top of which we have a model running on those features. So what I was trying to do is not wrong. So let me just go back. Let us just simply execute random search for some other thing. Let's just do regression and let's just select maybe a ridge regression or something. Okay. So I'm selecting where is ridge regression. Scale on API reference RIDGE. Okay, we have rich classifier here, and rich regression doesn't actually have regression in the word. Okay, fine. Let's just import that model. So from a scalar dot linear model. Where am I seeing that? I'm seeing that in the tab here. So I'm typing it from the tab. Linear underscore model. Import, we have to import rich. Okay. Then we say model is equal to RIDGE, and let's just execute this. Now if I do vars of model, what does model have? Model has alpha something something, and in this I want to see shift tab of this thing. Here is a parameter which is alpha. Okay, I want to find out best alpha value. What is alpha and something, this thing we will have to go in detail after you learn the algorithm yourself. Here we are just trying to teach you the framework. This is a kind of like a framework of trying to, just a second, a framework of trying to go through the whole model. Okay, just a second. Okay, so Jan,
Yes,
am I audible? Everyone
I
has
hear
left.
you. I hear you, Ajinkya.
Everyone has left. What should we do?
What do you mean everyone else left?
Yeah, I think I'm just checking on the this thing. How many people are live? I don't see anybody as live.
I have 13 people watching.
No, it's like I checked this thing on the YouTube live. It is saying no one is live, no one is watching.
No, I have
Oh, okay,
people, and people say
okay,
also in the chat they're watching. I see people watching.
okay. So one person I see. Okay, fine. So let me
Yeah.
know. Okay, cool. So let's continue then. So you see, like I said here, this was the framework I was trying to teach. The framework which is how do we understand an algorithm deeply. Now it's been some time since I have gone through the algorithms, and I was intentionally choosing the algorithms which I had not mastered, just to show you how is the framework of learning the algorithm. So now I would go about searching rich, because this is the first time. So rich regression, and I would be doing googling and trying to see, okay, what is the rich regression and why, how is it different, what happens there, which are the parameters, how it is implemented. Then maybe go in the algorithms and understand how it is executed, and stuff like this. So constant googling is how we kind of like simply learn what is happening, how it is happening, and stuff like this. Okay, so going back to here, the stuff I wanted to convey was, how do I do grid search? Okay, so here the grid search was, where was it? The grid search is grid hyperparameter optimization. So hyperparameter optimization is this randomized grid search. It is present in model selection, something, something. Let me copy paste this part. Okay, let me copy paste the whole thing. Okay, let's just say maybe I think we might be able to say directly import. No, not like this. We have to do from this thing, import this thing. Import is done. Okay. Now we have to, the way this thing randomized CV works, we have to actually create a grid. Okay. So it's nothing but a dictionary. So param grid, and this is in dictionary is created like this in Python. What is the character we want to optimize? It is alpha. And what's the grid here? Let's just make it uniform. Okay, so what this creates, oops, uniform is uniform distribution. Uniform distribution, yes, it is present in SciPy. Uniform distribution of random variable. It is also present in NumPy. So NumPy uniform. You see, uniform, numpy and scipy, it is present in both. So I can say numpy.random.uniform. So I can choose either. Okay, which one should we choose? Let's just go into scipy and how is it doing uniform? Uniform this thing. Okay, let me just choose scipy, just randomly, but I could also choose numpy. So what I'm going to say, I'm going to say import scipy.stats import uniform. You see, I'm checking this from this tab. SciPy starts uniform. So as you can see, everything is experimentation. Okay. I am just checking, looking at the output, going back, trying to change the code. And if you do this approach for, let's say, few weeks on different types of data you create, different experimentation, or even 1 week is more than enough to get a thorough, deep understanding of the algorithms you have chosen. Choose 5 algorithms at most in the beginning. Okay, you'll get a deep understanding of the algorithms you have chosen. You'll understand which parameters are important, which ones are not, and because you are doing and then going back to the code, and then in the code you are trying to check. Oh, this is the impact of the decision I made. Oh, that is the impact of decision I made. Stuff like this relate the theoretical understanding to the practical thing which is happening here. Okay, so the slide where I'm trying to kind of like come to is this. First, understand the algorithm as a theory, then try to understand when that algorithm is good choice and when is not a good choice. How do I do that? Working on the data, the custom data set which I have created. There I just have to try different experimentation to find out which one is a good choice, which one is a bad choice, which situation is good, which situation is bad. Stuff like this. When we do all this, then we actually understand all the situations. Okay, that's the deep understanding. And then we have to understand and try out different experiment: impact of noise, impact of normalization, outliers, different data, what is the execution time. All of these experimentations, this is the meaning. This is how we kind of like understand and go into details. If all these, okay, let me just go to slideshow thing. Monitor, always use a primary monitor and don't use presenter view. Now my setting is good. Now I'll check presentation. I think this will not use my secondary monitor. Perfect. Okay. So this is how you kind of like go around going into depth of the understanding. So this logic is actually applied for all the algorithms. Right now we are still on this factor where I'm trying to do grid search. Okay. Now we have created. Let's execute this thing uniform. Let me print out param underscore grid. Okay. Let me say param underscore grid dot. Here I want to print out alpha. Ha! This thing. How? This is how the distribution thing is. Okay. I would have thought there would be value here. Let me just do var soft here. And okay, the argument says this. It is, the distribution thing is starts from A, reaches until B, and there is certain distribution thing. Oh, okay, fine. And how's the randomized CV used? I just want to use it like this. So have I imported that? Yes, I've imported that. Let me just do this. What it is doing, it needs an estimator. What is the estimator? It is saying tree. Now I'm just going to write it like this: estimator equal to tree, so that it is easy to understand. What's the next thing? It is expecting param distributions. What's the param distribution? Which is nothing but param underscore grid. If I had multiple variables, I would be kind of like creating this grid thing of those multiple variables. Okay. Maybe let me go to randomize CV and maybe let me just check what is the example. So some of the examples I could see, here. This is the example, this thing in the documentation itself. So here also the stats was used. Parameter distribution, this is how it was created. It showed go from 0 to 1. Oh, that was better. Instead of we're taking it as default. It is also checking alpha. So and the distribution is log uniform. Okay, cool, interesting. And then randomized search is like this is the sentence. Parameter distribution, this dictionary is said, and this iterations is given. So we are correctly implementing it. We are correctly calling it. So param grid is this param grid, and I want to give an iteration. So n iter is equal to maybe 100. You have to try out lots of permutations and combinations. And yes, I want to give random state. Random underscore state is equal to 7. Let me just do this enter so that it can be read in one line. Okay, randomized search, and the output is R search execute. Wow, it was immediately executed. Now let me just the way it works, like you have to call R search dot fit on the data which is X underscore train and Y underscore train. What happened? There's something wrong. There is something wrong. Invalid parameter for this thing. Okay. Right now it is decision tree. Ooh, you are right. We should not be using model is equal to rich. Oh, we have to give model here. See, this is the model we give. And when we call it on the data now, and this is actually calling. This is trying out lots of permutations and combinations of the alpha to actually give us which one is the best combination. So in the machine learning modeling, we do hyperparameter search. We find out a good algorithm. There are for every algorithm there is going to be a better hyperparameter search. We are going to shortlist a few algorithms, then we can either choose the best algorithm out of them. This is how the ML modeling proceeds. Excuse me. So this is how the ML modeling proceeds. Okay, this thing has executed. Now, how does this R search work? Let me do vars of R search. Random state scoring. This thing CV error score. Oh, best score. You see, best score is a variable. The best score is 0.9. This is quite good. And then the best parameters, as you see here, you see by calling vars variable, I have immediately understood how my randomized CV works. In the randomized CV, there are two variables which contain the best permutation and combination of the parameters which I have given it as an input. Okay, here right now there are two, only one parameter which I have given, only one parameter. Okay, so in that one parameter, it is going to just give me the best combination. If I had three different parameters combination, which we had here, this is going to try out different permutations and combinations for average, element ratio, and alpha. So all of this permutation and combination will return a good combination to us, which we will then use in the final thing. Okay, and then let's just kind of go take a simplest thing. Let's take a simplest thing and kind of I had created a score. We can kind of try out different algorithms. Excuse me, I'm having a bit of acidity, so here this is how the way this work, ML modeling. We try different algorithms. We try to find out which algorithm is the best choice. So data is as is. We try, let's say 5, 6, 7 algorithms. Out of the 7 algorithms, we try to find which one has the least testing error. Okay, which so anything which has high testing error but low training error is overfitting. We are trying to find optimal fit, and out of optimal fit, maybe there might be 3 optimal fits, out of which one might be the best. For the best ones, we do hyperparameter search. Okay, this is how we kind of go through the entire process of machine learning modeling. And what happens internally, here we have to be totally conversant with the tool. We have to be totally conversant with the tool, but we also have to know the understanding of stuff like this. The first part was, okay, if it is overfitting, what happens? How do we check overfitting? We have already seen training error is less, testing error is high. Then how do I have to overcome overfitting? The reduce the model complexity. Just a second. Yes, I'm back. So I reduce the model complexity, and that's one way of dealing with it. The other way is like keep the model complexity as is, add a regularization. So regularization is nothing but a penalty. It is nothing but a error correction mechanism. So there are two types of regularization, L1 and L2. They penalize based on the error. L1 penalizes as a square of the error, and L2 penalty is proportional to square of the error, and L1's penalty is in proportion to the error. If there was L3 regularization, it would have been L3's penalty is in proportion of cube of the error. So you can simply search what it is, how we can go about doing that, and that is nothing but regularization. So where do we put L1 and L2 regularization? Or there is other concept called as now early stopping. Early stopping is like then we have to go into gradient descent part. So first level is getting a complete hang of important concepts and knowing how to use them and when. And then there is a different thing like, when do we use early stopping? What is the exact meaning of early stopping? How does it relate to gradient descent? All of these concepts. So when we kind of like reach that level, that is when we have truly, that is when we have truly reached a very conversant state of the machine learning knowledge. Okay, so there is a very complex framework here in the ML modeling. So what I want to do is like I want to share a Evernote thing where I have created this document wherein while creating the model we start with trying different models, optimization, and blah blah blah. So just a random dump of the stuff which I have been thinking. This is what is present here. If you want, you can find it by following this blog. Okay, it is is.gd. I think it is QUHAMA. So let is.ged/QUHAMA. Yes. And let me not remove the underline here. Did it? Okay. Now it works better. So www.is.gd/QMHA. Maybe I should change font so that the Q is visible as Q. Semi-bold. Okay, so this is the link I would recommend. And here, some of the framework is present. I'm going to update this framework with, more approach, and the framework approach is what will be kind of like the final level of the advanced machine learning experimentation. Okay, so this was the kind of like approach we could go into gradient descent. We actually have slides. I have the material. And then with gradient descent, we'll understand, how to, what is early stopping. Then also in the gradient descent, we can understand regularization. So there are few key terms which we have to understand. For every term, there is going to be a slide deck rather, not just slide. But that becomes too complex for an overview session like this. Okay. So let me see. This was what I kind of like had in mind for the day. I'm actually having very high acidity. That's why I'm kind of like trying to wind up a bit early. Otherwise, we would have continued for, add some bit more material, but I don't think I'll be able to take that. Okay. For now, this was actually quite more than enough. We went into depth of what is the approach to do any kind of like algorithm, started from scratch, tried a lot of stuff, didn't go into much basics, but we actually on a real data tried different stuff. And we have to run the experimentation, like this. If you go back into the slides in the video, you should see what kind of experimentation framework you should be following. And when you follow that framework, that is when you truly understand and master algorithm. Okay, so that would be my most recommendation for everybody. Otherwise, from my side, I think we are done for this webinar which we have.
Thank you, Ajinkya. I'm gonna take over. Yeah, thank you so much, Ajinkya, for leading the session. It was great. This time we learned more about advanced ML modeling. I hope everyone found this webinar interesting and helpful. Of course, the recording of the webinar will be available on the YouTube channel, so you can go back and rewatch it if you want. If you have any questions, please also don't hesitate to message us, send us an email, or questions through one of our social media channels. Also, please follow us on social media. We continue to post interesting updates, news about what we are doing, and of course, also more content. We will have more sessions, more webinars going forward. I will send out emails. We also post them on our social media channels. So please sign up, join us again. Hope you had a fun time. We definitely did. And everyone have a good night, good morning, good afternoon, depending where you are in the world. All right, everyone. Thanks for joining. See you soon. Bye.